All right, so we've made it to the last checkpoint of this chapter. In the previous checkpoint, we learned how to extract coefficients from the results of the CCDC algorithm. And for that, we use a lot of array image functions in order to index the position of the segments that we want, the position of the coefficients that we want, and then we use that to load them into the map. There is another way that we develop to facilitate doing that process. And that's what we're going to be looking at in this checkpoint here. And so you should be familiar with this upper part by now. We load the palettes library, we load the utilities that we develop, we load the CCDC results, and we put them into the map. And so in the previous checkpoint, we wanted to retrieve the coefficients for the middle of 2005. Right here, I'm using a different date, simply telling it I want to use the 25th of September of 2005. That is going to be my input date. And what I'm going to do here is that I am converting this date to the date format in which the CCDC results are. And so remember that that's fractional years, right? And so one of the functions that we developed was to convert between those three types of dates, fractional years, Julian date, and Unix time, and also to convert from this spring version of a date. And so we are calling this convert date function from the utilities that we loaded before. And we pass it a dictionary with the parameters where we tell it our input format is string date, which will be format 3. This is our input date, which I defined above. And then the output format is 1, which is fractional years, according to the documentation of CCDC. And so the result of that is going to be this date formatted in the format that we want, which is fractional years. And before I explain what these lines are, I'm going to show you this line over here. So this function is at the core of what allows us to manipulate CCDC more easily this way than having to write all these functions through array functions. And so from the utilities that we have above, we're calling this module called CCDC, and then we're calling this function called build CCDC image. And so in order for this to work, we are passing it the CCDC results that we have. We're passing it how many segments do we want to retrieve from those results. So this is defined in this function, in this variable called segments, segs, and it has 10 elements. So we're telling it we want 10 elements, segs.length. And we're also passing it bands, which are the bands that we want to retrieve from those results. So we are passing it all the band names that we use for that original CCDC run. And so this is going to give us this CCDC image. So what is this CCDC image? That is being printed here. And so the first thing that you're going to notice is that it has 650 bands. What this is doing is that it is converting the CCDC results from its array storage version to a regular image format with all of those things converted to bands. And so we're going to have segment 1, band blue, and the coefficient is intercept, coefficient slope, first cosine, first sine, second cosine, second sine, third cosine, third sine. So remember, each of these cosine and sine values are the harmonic pairs. So this will be the first one, this will be the second one, and this will be the third one. And we have the same thing for the second segment, third segment, fourth segment, and we have that for every single spectral band, for every single coefficient, for every single input of the CCDC results. And that includes the RMSEs, that includes the magnitudes, that includes the start and the end, timing of breaks, etc., etc., etc. So why are we doing this way? For us, it was easier to write this function to convert it to this format, because then it's easier to operate with this image and find things in this particular way. It's not the only way. I want to emphasize that there's other ways, and there's other utilities out there that allow you to interact with the CCDC results, but this is the way that we are demonstrating right now. And so we have that image here, and I'm going to jump to line 48, because once we have that image, what I'm doing here in line 48 is I'm telling it, of all those things, I just want to obtain the coefficients, and I want to obtain the coefficients for a particular date, which is the formatted date that we defined before. And so for that, we're using this function called getMultiCoefs, which, as the name implies, allows us to retrieve multiple coefficients from CCDC. And so there is documentation associated with these functions. You can look for that. The links to the documentation are in the chapter, and they're also linked to the tools that I demonstrated before. But what this function is expecting is the CCDC image that we created in the very long format, the formatted date, which we said before was for 25 of September 2005. We're telling it which bands we want, which we are defining here. I just wanted to give me these 4 bands. I'm telling it which coefficients I want. I'm telling it just give me these 3 coefficients, intercept, slope, and it's technically not a coefficient, but it sort of behaves like one. So that's the RMSE. This true here is to convert the intercepts to normalize the intercepts. And so I'm going to go back here to be able to explain that concept. So the intercept of the segment is the value where that segment will intercept the y-axis. And so if I extend, for this example, if I extend the yellow segment to touch the y-axis, it's probably going to be very close to its actual value, which is 0.15, because this segment has a slope of almost 0. But if I take this green segment and I extend it to reach the y-axis, it's going to be a really high value. It's going to be like 0.45 or so. And that value is not really representative of the intercept of the segment, which, if you look at the middle point of the segment, should be around 0.22, more or less. And so what we do is that instead of retrieving the actual intercept, we retrieve the intercept for the middle point of the segment that we are looking at. So that should be a value, in this case, of like 0.2. And so what this flag of true is telling it is, yes, we want the normalized intercept. We want the intercept for the middle of the segment, because that's what we're interested in. And this is what this is doing. We pass it the list of segments that we defined above. And then we are using this flag called after. And so this is for the following reason. Let's say that you request the coefficients for this date right here in later in 2007. So if you request the segment for this point in time, it is not going to intersect any segment directly. And if we don't do anything about it, it's going to retrieve us an empty or a null value. And so we might want to tell it, okay, if there is no segment, find the closest segment either after the date or before the date. And depending on what your interest is, you might want to pick one or the other. But in this case, I'm telling it, give me the segment after if when you look for that date, there is no intersecting segment. And that's what this is doing right here. And so once we have the coefficients, I'm printing the coefficients. They're shown here. And you see we have each of the spectral bands that we requested and each of the coefficients that we requested, which include the intercept, the slope, and the RMSE. All right, so once we have these segments, once we have the coefficients for that date, then we can visualize them on the map. And so we first look at the slope in the red. So that's right here. So higher values would show in brighter colors. So slope is going to be representative of the trend of that pixel. And so, for example, in the shortwave infrared, if you had regrowing patterns, you would see a slope that is negative. And so you can use that information to understand how your landscape is changing. We also load the RMSE in the near infrared. And so you see that more stable places like forest have lower RMSE values, so they are darker than places where you've had transformation, which are going to show higher RMSEs or brighter values, because those are more dynamic and display a lot more noise, among other things. And one thing that we can do is we can request the intercepts for the red band, the green band, the blue band, which we already requested, and we can visualize them as an RGB image. So that's going to be a real color image shown here. And so you see that it's it looks pretty much like a real color image, because we're passing the red through the red filter, the green to the green filter, and the blue to the blue filter. Because we're using the intercepts, and the intercepts are representative of something close to the average or the mean reflectance value for a given segment, then this is going to give us a snapshot of how that place looked for that particular time that we requested. So remember, here we have the intercepts that intersected the segments in the year 2005, month 9, day 25. And so what we see right here is kind of a snapshot of the landscape in that particular date. And so this is one of the great things about CCDC, that it works a little bit like a time machine. And if you run CCDC between 2000 and 2020, then you could go back at any point in time and retrieve an image like this and be able to reconstruct the history of transformation without any clouds, without any major artifacts, and just a clean representation of how the landscape is changing over time. Now, I mentioned very early on in this presentation that we were not going to cover the classification part of this, but one way in which you could use this data to in a supervised classification procedure will be simply taking the coefficients that we already defined here, that we're extracting for the year 2005, And then you could collect training data of things that look like the classes of interest for that year. And then you apply those to these and the rest of the segments in your CCDC stack to create a classification. But again, that's beyond the scope of this chapter. And so with this, we conclude the overview of the CCDC chapter to interpret time series of Landsat observations.